All right, so let's get started. I'd like to welcome you for today's lunchtime talk. Before introducing our speaker, I'd like to remind you of the events this week and the next week. On Friday, Ryan Neft, who is a Center Visiting Fellow this semester, is going to be giving a lecture in the philosophy of linguistics called Structures and the Spatial Sciences, a case of linguistics. And on next week at noon on Tuesday, March 23rd, Reid van Bork, who is also a Center Fellow this semester, is going to be talking about a causal interpretation of measurement models in psychology. And on Friday next week, we have our second annual lecture series talk given by Hélène Landry from UC Davis on the philosophy of mathematics. If you are interested in any of these lectures, please go to the center's website and look for the calendar. And on the calendar, you'll find a link to register and you'll receive an invitation to join us for this Zoom presentation. All right, that's it for the event next week. Today, it's my great pleasure to welcome Nick Huggett, who is going to be talking about missing the point in non-commutative field theory. Nick is a distinguished professor at the University of Illinois at Chicago. He has published widely in a range of topics in the philosophy of physics. He has published several books, including Everywhere and Everywhen in 2010 with OUP. Currently, he is leading a Templeton-funded project, Spacetime After Quantum Gravity with Chris Vustrich. And I recommend, if you do philosophy of physics, to have a look at the website of the project, which is www.beyondspacetime.net, which is really interesting website. Please have a look. And he's working on, I believe, but he can confirm, on 2 books out of nowhere on the emergence of space and time in quantum gravity, and True Motion on the absolute relative debate in early modern physics. I don't know whether you're still working on them or whether you're too busy to really work on 2 books at the same time. In any case, today, and last but not least, of course, Nick is a senior visiting fellow at the center this year, and we're really delighted to have him at the center. It's been a real pleasure to be able to talk to him on a regular basis. Nick, the screen is yours.
Thank you. Thanks, Edward. Yes, and it's equally been a real pleasure to be at Pittsburgh, at least virtually, for the semester. It's been great. I guess, yeah, what you say about the books, let's just, I guess, to leading order, that those are true. Those things are true. I won't go further now. So I'm going to talk today about some joint work that I've done with Fedele Lizzi and Tushar Menon, who I think are here and may be around to answer questions with me at the end if anything comes up on theirs. So I'm going to talk about part of this joint project. And I think I should note that Tushar is actually talking about another part of it on Thursday in the Oxford Philosophy of Physics seminar. So I invite people to come to that as well. Or maybe it's not the Oxford. Anyway, so let me get started. So, oh, rats. Okay. I meant to make a copy and post of the slides and post them in the chat. I'll do that quickly at the end. You'll have to just follow along for now. So first of all, let me just give you a sort of overview of the goals for the talk. So, and this will also be by way of explaining the title a little bit. So first of all, I want to obviously explain what non-commutative field theory is. So explain how it's a generalization of ordinary field theory and ordinary geometry to non-commutative geometries. Then I'm going to argue that it does not a non-commutative space does not contain arbitrarily small regions. There's a smallest region that you can have in such a space and how that makes sense. And then conclude in that sense, it does not contain points. I can't reach points because there's smallest region. From that, argue that it is essentially non-spatial. which then raises the question of how it might be that, if this is a candidate form of theory for physics, how might it yet appear that the ordinary spatial physics, the space that we experience and that physics, quantum mechanics, general relativity describe, emerge from this non-spatial structure? In some point, that's the sort of philosophical payoff here, is to find a test case for considering how we might understand space-time, the emergence of space-time from something non-spatiotemporal. That sort of idea is at the back of a lot of the work I've done over the last decade. Okay, so those are the goals. The letters here kind of correspond to some sections that I have for the talk. So the general strategy here is going to be to present some classical physics, a classical formulation, and then deform, and we'll come to see a bit more what I mean by that, that structure to non-commutative physics and geometry. I should say there's going to be some probably unfamiliar mathematics, or unfamiliar to many people in the audience mathematics. I'm going to try to present most things in an intuitive way. I hope enough for people to understand the payoff of what I'm saying. But I imagine there'll still be just kind of questions about what's going on and about the mathematics. I am happy to answer those in the questions as well. Some parts I'll put in a little bit more because I know there'll also be a little more technical detail, because I also know there will be people in the audience who are more familiar with these ideas, and I want to make sure they understand how what I'm saying fits into what they do know. So we're interested in the existence of points, and we need to somehow make this question physically significant. And our strategy in the paper is to do it through particle localization. The idea is something like, well, what, physically speaking, is a point? It's somehow the smallest place anything can be. And then a particle is the smallest thing one can sort of have. We're going to be doing field theory. So actually what it turns on formally is really going to be how small can we localize a field. Okay, so let's but focus on particles, and suppose we're thinking about measuring describing the location of a particle. If it's been measured, well, that was with a real measurement, then there was some limit to the resolution of that measurement. Every measurement comes with some basic, level of resolution. And so the result of any measurement, and so our knowledge of the position of any particle, is always going to have some epistemic uncertainty. I think it's at this point, but, plus or minus a little bit. And then we're then going to represent such states epistemically, including the uncertainty in its position. And the natural simplest way to do that is through using a Gaussian. So I think the particle is, more or less at the point x0, but there's some uncertainty in my, where I think it exactly is, and that's parameterized by alpha, the width of the Gaussian. Okay, on this slide, I'm going to be just working in one dimension. In future slides, we're going to have to switch to 2 dimensions, but just to keep the expression simple, we're in 1 dimension for now. Once I have a state like that, I can now calculate expected values for observables. F is an observable here. This is the standard prescription. I'll just integrate their product over space. Best to explain that with an example. So if x is position, then of course the expected value for this Gaussian is going to be x0, which is sort of my best guess about where the particle is. We can also, another observable might be x squared. You can calculate its value, and it's what I've written here. And I did that because it allows us to compute the uncertainty formally, which is the difference of the squared expectation value and the expectation value squared, their square root. And you can check that's basically equal to alpha. And so again, alpha, as I said, reflects our ignorance in this case. It's the width of the Gaussian. Right? Don't worry about the square root of 2 factor. Okay, so it's sort of the size of our best guess, one can say. Now, I said in the setup that if I perform any measurement, with an apparatus, that's going to have some inbuilt, resolution, some level of accuracy. There's always going to be error bars. But classically speaking, there's no physical restriction on building a better piece of equipment with narrower error bars. That makes me less certain, that makes me less uncertain. More certain gives me better knowledge of where the particle is. And that's nicely reflected in the Gaussian formulation as well, because one can take alpha as small as one likes and still have a Gaussian, and that will reflect ever better pieces of apparatus for measuring position. So although any one piece of apparatus for measuring position is limited, there is in principle no limit on how good the how much we can improve the apparatus to make a better measurement. And so that's reflected in the fact that we can have Gaussians as small as we like, and in the limit, we can think of there being point localization. So that's the sense in which we will actually take it to understand points. We're not going to worry about there being functions that are actually piled entirely on a point. We'll understand what a point is as the limit of increasingly good localizations of finite localizations of particles. And that all makes perfectly good sense in the classical case. Okay, and it's exactly that that's going to fail when we switch to non-commutative spaces. Good. So to get to the non-commutative spaces, we're going to have to first look at classical geometry from a probably unfamiliar to many point of view, not in terms of a manifold, as one normally does, but in algebraic terms. Okay. Once we have the algebra, we'll see how to deform classical commutative geometry into non-commutative. So let me explain these ideas a little bit. So, our intuitive notion of a field when we have a manifold is some kind of function, a map from points into numbers or other mathematical objects, which we take to represent field strengths, temperature, gravitational field, electrical field, and so on. Okay, so imagine taking the collection of such fields, and here we're going to think formally, so the functions that describe them, and just consider that set, the set of fields living on some manifold. And more precisely, they're smooth and complex valued fields. Okay, so for example, if it's a two-dimensional manifold with coordinates x and y, polynomials in x and y will then be such smooth complex valued fields. We can take finite and infinite polynomials in this collection, as long as they converge, and we will have functions like Gaussians. Incidentally, I am going to use the two-dimensional Gaussian as an example here of a nice smooth function living on the manifold, and so an element of Cm. And this, of course, now would represent a particle localized in 2 dimensions, about the point 0 in this case, and again now with with uncertainty alpha, or alpha squared for the area in which it's located. Okay, but these are a couple of smooth functions, and so we just want functions of smooth functions of x and y representing different possible states of a field. So I'm going to make a sort of important distinction here to try to bear in mind. We should distinguish a function, say psi, which assigns a value to every point, from its value, which we might write as psi xy, at the point xy. So we have to be a little careful here on notation. Obviously, these are different things. The function is a whole configuration of value at every point, and that's distinguished from a value at one particular point. We often aren't that careful about distinguishing these, and often it's not important. One will often write x, psi of xy, for instance, as the whole function rather than its value at a point. But I'm going to have to go back and forth between talking about functions' values at a point and functions as a whole. So you'll see as we go on that it's important to keep this distinction in mind. All right, let's talk a little bit more about Cm, this set. So the first thing is that it's an algebra with respect to pointwise multiplication. Basically, if I take 2 smooth fields, psi and phi, and then at each point multiply their values together to assign a new value at that point, the effect is to define a new field, chi in this case. Okay, and that'll also be a smooth field. All right, so it's not just a set. If I include pointwise multiplication, just perfectly ordinary multiplication of the values at each point, it becomes an algebra. And perhaps not very surprisingly and not so excitingly seeming, it's a commutative algebra. It doesn't matter which way round I multiply the fields. Psi times phi is the same as phi times psi, and that's because I'm multiplying at each point, their values at each point, and multiplication is commutative. So that seems not very exciting, and CM seems like maybe not a very interesting object to be thinking about, except rather remarkably, it turns out that it uniquely captures the topology, and if you know a bit more about these matters, differential geometry, depending on exactly what we've put into CM, of the manifold. So this goes back to work by Gelfand and Neymark in the 1940s on C-star algebras, but the result that's relevant here is that there's a one-to-one correspondence between the topology and the algebraic structure. If you tell me what the algebra is, then from that one can infer whether the underlying manifold is a plane, a cylinder, a sphere, or an n-torus in the two-dimensional case. So it turns out there's actually a lot of information in that algebra. Okay. Moreover, one can define in algebraic terms other geometric structures, say the affine structure, the notion of what is a straight line in the geometry, metrical structure, and so on. These things can all be defined algebraically. And this point is exploited rather nicely by Wold in relation to general relativity. In his algebraic formulation of general relativity, he proposed Einstein algebras to do just to capture general relativity in just this algebraic way. Okay, so what this means is every algebra, to put it in a bit of slang terms, we can do geometry without a manifold in a certain sense. Okay, every geometric fact then, in fact, corresponds to an algebraic fact. And this idea is an important one for understanding what's coming. So I'm just going to dwell on it for a minute. And I mean, instead of trying to give you details about how this works in the geometric case, let's just consider a very simple example, which will, I think, make the important points as well. So consider a much simpler algebra than CM, and it's the one I've written here. Okay, it consists of two elements, A, B, and a product written by that dot circle there. I'll just call it dot. Let's just call it times. And so we have, with respect to that dot, I'm just going to define, this is the structure of the algebra. A times A is equals B times B equals B, and A times B equals B times A equals A. So I've done that without telling you anything about what A and B are. Okay, and so I've done it in a totally abstract way that only tells you the structure of the algebra, basically tells you, what the function dot times here is. Okay, so that's really what I mean by the algebra. It's that structure there. Okay, now if I also tell you, but this is an algebra for numbers and addition, then you will realize that dot has to be addition mod 2. Okay, A is going to be equal to 1 and B is going to be equal to 0. So 1 plus 1 is 0 plus 0 is 0, and so on. Alternatively, if I go on and tell you A is truth and B is falsity, and so you recognize that dot must now be a Boolean operation, then you'll recognize that it's the negated biconditional. Okay, so good. So, but these things, either addition mod 2 or this Boolean operation, these are then concrete realizations of the underlying abstract structure, the thing that they have in common that's encapsulated by effectively this table of the values of that expresses the the product here. Okay, and then the same story is then going to apply for algebraic geometry. you want to think about all the geometry is contained in the abstract pattern of relations, just as everything in these cases is contained in the abstract pattern of the relations between A and B. And then Cm, the spatial functions with multiplication, with pointwise multiplication, is just one realization, one representation of that algebra. But I don't need the representation, I just need the relations, the algebra to capture the geometry. Of course, that relates, since we're talking about space and fields seem to correspond to the world, from that point of view, the Cm is a very natural representation of the algebra, or if these are literally fields in space, that's a very natural representation of the algebra, of course. But again, it's a representation, a realization of that underlying algebra from the geometric point of view. And that's important to bear in mind because as we switch to non-commutative geometry, it's highly questionable whether there is a corresponding space to the algebra. We're just going to be left with the algebra. Indeed, that's where we're headed to. So to sort of see how, just remind you where we are. We've been talking about commutative space described by a commutative algebra. And actually we can capture that in the two-dimensional case by the simple statement that the coordinates commute. X and Y are fields. At each point, X returns the X coordinate of the point, and at each point, Y returns the Y coordinate of the point. Then, of course, because these commute, their polynomials will commute, as we saw before, and so all the functions will commute. So this is how we express that our whole algebra is commutative, just by talking about these base elements, the coordinates. A non-commutative space is obtained by simply just moving to a non-commutative algebra. If you're a mathematician and you have an algebra that commutes, the thing you're going to try is making it non-commutative and see what happens. So deform it to a non-commutative case. So I'm now going to say these things, the coordinates in some sense, no longer commute. Okay, if I have X times Y, and it's not the same as Y times X. If I subtract them, there's some finite residue. So let's explain this a little bit. I'm going to put hats essentially to indicate that these things do not commute. Okay, and I am this, but still they're going to have the dimensions of length. They're both lengths, and so theta must be have the dimensions of length squared. It's an area. It's a fundamental constant. And it's also going to be an invariant area. So we're not really going to be considering relativity here, but it does violate, it will violate relativity. And so what's going on here then is analogous to what we have in quantum mechanics, where one would have momentum and position, and their commutator, this object I've defined with the square brackets here, which is the difference of their products, you would expect to be equal to IH bar Planck's constant. Okay, so theta is not necessarily H bar, but there's a lot analogous to that case. Okay, so let's push on with that. So suspend intuitive understanding that I mentioned before about what a field is in terms of a function. So we're going to have to come back and think about exactly what a field is. But the convention is to still call the elements of the algebra fields, even though they now have hats on. Okay. So, but we are of course going to find that the algebra that we now get is going to be non-commutative, as this simple example shows. In the commutative case, the classical case we were looking at before, x times y is the same as x times y times x. But you can see the non-trivial commutator makes that not the case. If I take x times y, well, the x times y, you can see from above, is going to be equal I theta plus yx, and that's not equal to x yx when I have the hats on. Okay, so our algebra, the fields are not going to commute anymore. And so we have a non-commutative algebra. And so in this case, well, so x squared y would just be one element of the algebra in the commutative case, here I have two elements of the algebra because of the non-commutativity. Remarkably, and this is sort of the important fact that sort of makes this whole work, is we can still do algebraic geometry and field theories. So much of the structure of the algebra is going to be different now that it's non-commutative, but much of it is still going to be the same. And remarkably, the structures we need to do geometry, the things we need to do physics of field theory will still remain. Somehow putting things into algebraic form, and considering geometric structures algebraically, those structures are all saved when we go to a non-commutative case, which is pretty surprising and interesting and useful for what we're going to do. That doesn't answer us the question about what is the space like now? What is space like in this geometry? Because we've just got the algebraic formulation. And the question that I'm sort of pursuing here really is to do with figuring out what does space look like that corresponds, how can we think spatially when we have the geometry of that space described by a non-commutative algebra. And in particular, there aren't going to be points. Okay, so the result of this, the space that we've come up with, the geometry that's described by non-commutative geometry, well, we can call it non-commutative space. We'll also call it quantum space. And our question is going to be, what is this actually like? So a couple of points about that usage. First is, although I'm calling it quantum space, as I've noted, H bar hasn't been involved. It's not quantum in that sense, in the sense of ordinary quantum mechanics. There's a new parameter, which you might set H bar if you wanted, but basically it'll just be numerically equal to it. Better, if you think about, if I have physics, it's usually standardly encoded in an action, and then I get classical mechanics by applying Hamilton's principle, demanding that the action be minimized. Or I can get quantum mechanics by using Feynman's path integral principle and calculating amplitudes that are weighted by the exponential of the action. Both things are open to me in quantum space, in non-commutative space. And so I can, in a sense, have classical fields in quantum space or quantum fields in quantum space. For the first part of the talk, I'm going to be considering classical physics. Always silence your phone. In the last part of the talk, I will switch to quantum fields. I should also note that physics community is mixed on whether they're willing to call non-commutative spaces quantum spaces. Exactly for the reason I've just mentioned. We're going to use quantum space, as I said, because it has this nice pedagogical feature that for those of you who know some quantum mechanics, will have a sort of jump on understanding what's happening, because we can just import a number of quantum ideas and interpretation into the current setting, precisely because we're dealing with non-commutation. The first example of this is there are going to be quantization and dequantization maps that take us between classical functions and non-commutative operators. So if I have some classical fields and I want to know what their quantum versions are, if I have a classical state, for instance, a localized particle, and I want to know how to represent it quantum mechanically, there's going to be a standard quantization map that's going to tell me how to do that. I won't give the maps here. I will just quote the important result for us. But basically, we're going to have a way to translate between classical systems and quantum systems. So, in fact, if we translate our classical localized particle in 2 dimensions into quantum mechanics, here is the result. I'll mention Lorenzo Leone in particular. We're just quoting this result from some other work. Lorenzo Leone was an undergraduate student of Fedele's. This is part of his undergraduate honors thesis. So I'm very happy to acknowledge him. So take a classical, epistemic state of a localized particle. I'm hoping you're seeing me moving my cursor around. This is the 2-dimensional version of the Gaussian we looked at before. It's a particle, centered on, our guess about its position is centered on 0, but we think it's in an area. Now we're talking two-dimensional of area alpha squared. That parameterizes, again, our ignorance of exactly where it is. Okay, so in quantum mechanics, that becomes an operator. We put a hat, we're going to end up with a hat on it. It's going to be a non-commutative object. And we can find a basis in which it can be represented as a diagonal matrix. So if you know quantum mechanics, you'll know what I mean. If you don't, it doesn't really matter. I can just tell you it can be represented by this matrix, and we can find a way of writing it in which it's diagonal. So I'm now going to appeal to standard quantum interpretation. Again, it's not important to know a great deal about that. Nice, it's good if you do, but not necessary. The important aspect of the quantum interpretation is the following. If I have a density matrix, a state, written as a diagonal density matrix, those diagonal elements represent the probabilities for finding the system in given states, the eigenstates of the basis. Okay, but those diagonal elements have to be probabilities, and so they must be positive. Now, it's quantum mechanics, so we generally take these probabilities to be ontic rather than epistemic. How different people interpret them in different ways. And at this point, I will just invite people to fill in their preferred interpretation of quantum probabilities. I think everyone will agree, however, those probabilities do have to be positive if this is a physically respectable state. Okay. And that's the important thing, because now we can look at this matrix and we'll see the following. Well, as long as alpha squared is greater than theta, remember, theta is an area. It's the area that appears in the commutator. Alpha squared is more or less the size of the area to which a particle is localized. Okay, it's the uncertainty in the particle. As long as that is greater than theta, you can check the first three elements. This is an infinite matrix, but the first three elements are the same as all the others. Alpha squared is greater than theta, so we will indeed have positive numbers all the way down the diagonal. So that's good. And that corresponds to the case where the particle is not localized within the commutation or the non-commutation area. The case where alpha squared is equal to theta is special. The first element you can see becomes 1. Everything else becomes 0. That's actually what we consider a pure state. But look at that second element, and you can see what's going to happen in the other case, in which alpha squared is less than theta, the case in which the particle is localized to a region smaller than theta, an area smaller than theta. There are going to now be negative terms, and you can see that for the second element down the diagonal. I have all positive except in the parentheses there I have alpha squared minus theta, and of course that's now a negative number, but I can't have negative probabilities in my density matrix, so this state is unphysical. I can kind of write it down. I can apply the quantization map to a classical state that's localized below theta, but the quantum state is going to be unphysical. There really are no such states. Good. So just to sort of reflect on what we've said, and an epistemic classical epistemic state, or sorry, an epistemic state in classical space, as we saw, can be localized arbitrarily. I can make my Gaussian as narrow as I want. But in quantum space, the corresponding ontic state is going to be unphysical if you try to localize within theta. Okay, it's in 2 dimensions. If I try to localize think of a state localized, of a particle localized to a region smaller than theta, I get something that's unphysical, which is just to say states in quantum space cannot be arbitrarily localized. You see explicitly here that theta is the smallest you can localize the position of a particle. And so we can't get points as we did in the classical case. We can't take the limit of smaller Gaussians, of more localized states, to define what a point is. The points just don't exist as limits. Theta is the smallest region to which a particle can be localized. Okay, So that's the first demonstration that there aren't, in this sense, points in non-commutative geometry. Indeed, that there's a minimum area. So in the next set of slides, I'm going to come at this from a slightly different angle, make the same point in a different way, and illuminate what sort of happens if you try to localize a point, a particle more. But to do that, we're going to need to introduce a different framework for non-commutative field theory. We're going to use the Weyl representation, what's called the Weyl representation. And the idea here is, wouldn't it be nice if we could do even non-commutative geometry in a manifold? We have lots of nice mathematical tools, and once we have a manifold, we can use the calculus, and that's really good because that's very powerful. So what if we take a nice smooth manifold, a plane, say, and cook up a new product such that x times y is no longer equal to y times x, but indeed, and such that the commutator between those products is going to be equal to I theta. So that's the idea that we have here. Let's define a new product and denote it with the star, the symbol star, and a new commutator as I've defined it here. Okay, so x star y minus y star x. And we want it to be equal to I theta, so that we're replicating the algebra that's describing our space. Okay. So we're going to take this statement and try to find a star that satisfies this relation. And actually, there are various ways of doing it. In our paper, we use what's known as the Weyl star, which looks like this. If I take phi star psi, that's going to be equal to phi dot psi, where dot is the normal pointwise multiplication, and then some extra terms, which I won't burden you by putting them in. But you can find them in many places, for instance, in our paper. Okay, but there's going to be extra terms that ensure that x times y no longer commute with respect to the star product. So, okay, just to make sure everybody's on the page here, it's of course crucial to contrast the star product with the ordinary pointwise dot product, which of course the functions x and y do commute. All right, so I've got my manifold, and there are sort of two products floating around: the familiar dot product, pointwise multiplication, and then any two functions will commute with respect to that. But what's actually going to be physically relevant is the star product. So I should not use that dot product pretty much ever. And instead, anytime I need to multiply, if I'm trying to represent, find a realization of the algebra, I need to use the star product. So for instance, elements of the algebra are going to be represented by the star product. So I think this is an example I had before. The element of the algebra, A x hat, B x y hats, C y x y hats, is going to now be represented by, each time I'm multiplying in the algebra, it's going to be represented by the function ax plus bx star y plus c y star x star y. And that is now a function on the manifold, where a star is this funky product that involves pointwise multiplication plus a load of extra terms that we won't detail here. Okay, and so we can reproduce all the elements of the algebra, all the polynomials, obviously, and then there's a way of completing the polynomials for other functions, including Gaussians that you want. So I just want to emphasize, from an algebraic point of view, of course, what's going on here is we just have a formal representation of the elements of the algebra, and we need to keep in mind that there's a difference between their algebraic significance, the object that we're trying to represent in this manifold way, and their representational significance. What does it mean that these things are now functions on a manifold? Okay, they're really representing elements of the algebra. So I think this might lead to the thought that, look, well, the Weyl representation consists of fields in the sense of functions on a manifold, right? And that manifold admits coordinates that commute with respect to the dot product. So should we not think of non-commutative geometry, non-commutative field theory as really living in this pointful space, this ordinary manifold that has points, unlike the pointless non-commutative space? And it's just that physics, for instance, in the action in which we would write all products with a star product, use the star product, not the dot product. But this idea really can't be right. This is a really kind of sort of misunderstanding of what's going on here. To say that we should use star rather than dot to do our physics and to do our geometry is to say that the non-commutative geometry contains, the algebra contains all the geometry, because that's what we're representing, and that the action in that algebra, written in algebraic terms, use that action. That's what it is to say that the star product is the physically relevant one. But we've seen, once we're committed to just taking the star products seriously, then we end up with the algebraic relations and algebraic structure that we saw before, in which case we've already seen there are no states in which fields are defined below, no particles that are localized within the theta scale. Introducing the star product is enough to get those results. There is not arbitrary particle localization, and in that sense, in that robust sense, no points as soon as we introduce the star product. It really is the same as just taking the algebra to represent our geometry. Okay, again, so if it's the physically significant product, the fields don't commute. There's no localization smaller than theta. And as we'll see in the next couple of slides, no measurements below theta can be operationalized either. So despite the existence of the Weyl representation, and this is really the payoff of the previous slide and the next one, showing the sense in which there are no points, is that we should take the Weyl manifold as a representational device. And although it has points, these are really surplus structure for representing the algebra. There's no physical, we don't get any physical significance to them putting them back in. Okay, so to make the, I want to, show now, as I promised, another way of seeing, use the Weyl representation as another way of showing what goes wrong if you try to localize particles below theta and show sort of measurements smaller than theta, of accuracy greater than theta cannot be operationalized. So once again, we'll do that. First, we'll set up the classical case and then move to the quantum case. So classically, consider a specific position measurement that we're going to try and operationalize, a yes-no measurement position with a detector of limited accuracy. So the detector, this is a detector we can ask, is the particle here? And it'll say yes or no. Sometimes it'll say yes when the particle is there, isn't there. Sometimes it'll say no when the particle isn't there. It is there, excuse me. So it has limited accuracy. So suppose concretely we ask it, is the particle located at a point x lambda? Then we can write to the corresponding observable as a Gaussian. Okay, again, x lambda is our target where we're asking whether the particle is, but there's limited accuracy, and that's going to be parameterized by a number beta, which is generally which is the area in which we're really kind of looking to see whether the particle is. It expresses if I get a yes, it expresses the uncertainty in whether the particle really is at lambda, because it might really just be in the area beta. So now we'll now take our classical particle from before, so 2 dimensions. Sorry, I wrote this down. I've written this down in 1 dimension here. We imagine a 2-dimensional version of that. Oh, I'll back up. I'm working back in 1 dimension again. I'm going to plug our 1-dimensional particle back into this to keep things simple. So that was a Gaussian as well, whose uncertainty was given by, whose width was alpha, about a point x0. If I plug that in, and to keep things simple, we'll set alpha and beta, the widths of the particle localization and the widths of the apparatus localization, its accuracy, both to the same value, let my particle be peaked at x0. And then we can find the probability of yes is going to be given by the expectation value of lambda for the state rho, that integral that I put on an earlier slide. And if you work that out, it's going to be this Gaussian. And that means if the particles are much closer together, so the particle and the detector are much closer together than the uncertainty alpha, then I'm going to get, this is going to be nearly equal to, it's going to approximate 1. And so if they're really close together relative to their uncertainties, then I might expect the particle to say yes with near certainty. On the other hand, what if they're separated? I'm going to put in thetas here, even though theta has no significance in the classical case, just because I want to compare this case on the next slide with the non-commutative case. But what's important here is that I'm going to have the particle and detector represented by Gaussians of the same width. And I'm going to place those two Gaussians 5 Gaussian widths apart. Okay. In that case, well, it's easy to check that their products are going to be about 0 and the expectation value is going to be about 0. Okay, I don't expect the detector to find the particle if they're 5 Gaussian widths apart. All right, so what happens when we do the corresponding experiment in non-commutative space? And of course, in this case, now I have introduced the theta, I'll be trying to determine a position better than theta. Okay, so let's work it out. So same experiment in quantum space. So it turns out in the Weyl representation, if I use my quantization map, my translation from classical to quantum cases, Gaussians actually map to Gaussians. So it's going to, mathematically, it's going to look the same. I'm going to have a Gaussian rho representing a localized particle, which I'm going to try to localize within theta. And I'm going to have a Gaussian lambda that also I'm going to try and make more accurate than theta. And the important difference is I'm going to be using the star product between them. Now, we do have to work in 2 dimensions here. On the previous slide, I kept things simple and considered a measurement in 1 dimension. Here, we're going to be working in 2 dimensions. And that's, of course, because X commutes with itself, even with a star product, but it doesn't commute with Y. So to see the non-commutativity, we have to have at least 2 dimensions. So imagine a particle being localized into a very tiny area, and the same with the detector. And now we'll see what happens in the non-commutative case, which means for physical purposes, we have to use the star, not the dot product. Okay, so I'm going to, again, as we did on the last slide, consider a particle that is localized to an area 1/100th of theta. The width of the Gaussian then is 1/10 of theta. And I'm going to apply a measurement that's trying to detect whether the particle is in a region 1/100th the size of theta. Again, a width of, 1/10 of the square root of theta. Okay. So same as before, they're going to be placed, square root of theta over 2. So that's basically 5 times further apart than their widths. Very good. Well, you might think what's going on here. We've already seen that states like this, and so presumably observables like this, are unphysical. But it's instructive to run things this way to see what goes wrong in this kind of experiment. And basically, if we are taking the Weyl representation too seriously and thinking that the points are physical, what actually goes wrong to sort of back up the claim that I've been making that there are no points in the Weyl representation. Okay, so I've now got 2 Gaussians, and as functions on the manifold, they're 5 widths apart. And so as we saw on the last slide, they don't overlap. Okay, that these 2 functions on the manifold representing particle and apparatus do not overlap. And their product then everywhere is essentially zero, which is to say they don't see each other. Okay, so a bunch came up here. So they don't in the classic, thinking of them classically, they don't overlap. This is to say these two functions in the space don't overlap anywhere. But physically, we have to use the star product. Okay, and with respect to star, they do overlap. You will find them overlapping. So let's see that through. Now look at the graph that I have here. So the first thing is the product is actually going to be complex, even though the two functions are real. So we have the real and imaginary parts plotted here, but focus on the real part. The units the vertical units correspond to the value of the product. Okay, the horizontal units are units of Gaussian width. So each one of these is 5 widths of the Gaussians. Okay, so 5 times alpha, which is the same as beta. Okay, so now you can see what's going on here. So if you look at, say, 5 Gaussian, there's an asymmetry here because, of course, the particle and the detector are displaced on a line, which is running so more or less across the page from left to right, rather than back to front. So we'll look at the axis that runs from left to right, which is runs along the line between the two particles. So if one looks, say, at a separation of 5 units, the distance at which they're separated, we now see in these peaks here, a non-trivial product is obtained. Okay, so there the detector is still seeing the particle, even though they are 5 Gaussian widths apart. We can even come out to 10 Gaussian widths, okay, 10 times the localization, and we'll see non-trivial, non-zero overlap between the two of them. The product is still non-zero. In other words, the detector is seeing the particle, even though they're 5 Gaussian widths apart. And in some sense, it's seeing it even further apart, twice as far apart as they actually are. I mean, that doesn't really make any sort of physical sense, but that's exactly because we tried to describe things that themselves don't make any physical sense. Particles and detectors that are localized within theta. But the upshot is, operationally, these things would not be localized at all. Okay, so the detector sees the particle well beyond the region in which they're supposedly located. None of this makes sense. And there are other pathologies that you will see. The probability is imaginary. Other moments of the probability are going to be imaginary and negative. This does not make physical sense. Again, a reflection of the fact that there are no such states. And indeed, such effects are generic for similar measurements. And again, the problem is that we're acting as if there are fields within theta and that they're physically significant, but they're not. You can't shrink these things down arbitrarily. And so operationally, we've now seen you can't shrink things down to arbitrarily small regions. And so operationally, there are no points. Okay, let me move to a discussion. Just remind you about what we've seen before moving on to some philosophical kind of remarks about this. So I've explained to you what I mean by a non-commutative space to some extent. And what we've seen just formally is states supposedly representing localization with theta are unphysical, and that measurements that try to localize systems within theta are also unphysical. Those are the two results. So what we conclude from this is then, to make these, we've made standard assumptions about quantum probability. We will also really have in mind a mild kind of operationalism, a tempered operationalism, which doesn't say that quantities have to be defined by their operations, but they must have operational significance. They must make a difference to some physical process that can be measured. given that, regions smaller than theta, and in the limit points, remember theta is a finite area, anything smaller than that is unphysical. We can't take areas to zero, so there are no, beyond theta, I mean, so there are no points. So I just want to emphasize this has nothing to do with worries about delta functions and whether they really represent anything. There's a smallest finite area that has any operational significance. Okay. So, of course, it's logically consistent to insist that there are points despite all this. But just as it's logically inconsistent to insist that there's a preferred frame in special relativity, even though there's no structure supporting it, as there is no structure supporting smaller areas in non-commutative field theory, and just as there's no way to observe it, just as there's no way to observe a preferred frame, just as there's no way to observe smaller areas than theta. But the points have no physical significance within quantum non-commutative field theory, and there's no way to observe them. So in those significant senses, there are no points. But if there's no points, then non-commutative field theory physically is just not a theory of point-wise spatial fields. There are no points for them to take their values. And for me, this is really the payoff. If you like, what we've seen is we shouldn't be thinking here of space as sort of a given. If you're thinking about the Weyl representation and somehow rendered invisible by the star product, the way to think about this is there really is only the algebra, and it happens to have a representation on the manifold, but you should not take that representation too seriously. The elements of the algebra are really what's physical. And in the Weyl representation, they're not represented, they're represented by functions whose point values have no significance. Their only significance is, in fact, the full function, the full configuration over the manifold. Okay, so here's some questions that then come up. So I've started addressing this. What is non-commutative field theory a field of? It seems that it's a theory of an algebra. And then there's very interesting questions about what kind of ontology that has. What does it mean to take an algebra seriously as a physical ontology? Some issues we address in the paper. It seems like visualizability is very tied to spatial spatial pictures. But there's a small literature with which we agree that says, it's possible to understand a non-spatial ontology because comprehensibility does not require visualizability. And then we've done some exploring of how familiar philosophical positions might play out if physics is an algebra, various forms of substantivalism and anti-substantivalism. And in part because of the work, the Einstein algebras, people have done a little work on some interpretations here. I'm sure a lot of you have the question about what motivates studying such a speculative theory. And I do have a slide prepared on that for the next page, but given the time, I'm going to skip over that. And if somebody wants to be motivated, I will encourage you to ask me in question time, and I will show you that slide. Because the point I want to finish with is the following puzzle, which is really the one that's motivating me. The unit of physical significance is an element of the algebra, okay? Not point values of a field as they are classically. From the point of view of the Weyl representation, an element of the algebra is an entire field configuration, the full function psi, not the value of psi at any point. Well, how that contradicts how we experience the world and how physics describes it in terms of commutative fields, and in particular in terms of local experiments. We're not restricted to understanding only physics of the whole of space, but to local experiments, not point experiments, but in finite regions, not the whole of space. Yet, if we try to think, it's very hard to see how to read that off the Weyl representation once we've concluded that the the elements of the algebra have physical significance because, again, they're represented by complete functions, complete configurations, values of the field at every point, not at just some of the points, the ones we're interested in. And so that brings us to the question of space-time emergence. Okay, so here's the slide I am going to skip over and get over to the thing that gets me up in the morning and the question of space-time emergence. Where do we get commutative space-time from if what's underlying is actually an algebra? So of course we do work in the Weyl representation. We take the elements of the algebra and represent them by fields on a manifold. Again, I am thinking of the full function here. An element of the algebra is represented by a function, not its values at any particular points or subset of points. I am now going to switch from sort of essentially assumed classical fields to quantum fields in quantum space-time. So I'm going to be assuming in the background Feynman path integral principle rather than Hamilton's minimum action principle. And so here's a proposal that comes from the literature from a paper by Chaichian, Demichev, and Presnida, or CDP for short. Actually, in service of a different goal, they proposed a function from elements of the algebra, or Weyl fields, onto what they called physical fields. Excuse me. By which they mean the kinds of fields we actually observe in space. I'll just say P's here. And they define this function. So here's how you should read it. The value of the field phi p at x is given by this integral. You can see that x appears as a constant in the integral. And then there is integration over x prime, which is the coordinate, the parameter of phi w, the Weyl field. Okay. So the value of this phi p field at a point depends on what function phi w is. Right? It's an integral over all of space, so it's dependent on the whole field. But I also have this Gaussian, which effectively smears out any details about what phi w says around the point x in a region theta. So it actually smears out exactly the information that we think is unphysical according to our earlier analysis. That's what it does mathematically, but ultimately you need to think of this as a map from the algebra, from elements of the algebra, phi w, into point values of some physical fields, some observable fields. I'm going to add to this an ansatz. So formally, that's just a mathematical expression that defines a field value at each point. So here's how we want to interpret this, which develops it takes the idea of CDP in a slightly different direction. We want to say, so x prime clearly is the point, this Weyl representation parameter. X we want to interpret not as a point in the Weyl representation, but a coordinate of space as we experience it and as space normally describes it. So it's a new parameter. It's not a coordinate for Weyl space, and we interpret it as an effective spatial position. Okay, so there's a map. This ansatz uses the smearing to map functions, to map elements of the algebra to observable values of a field as we actually observe them. Okay. Of course, we're not saying that this field value itself makes down. What we're interested in is the whole field phi p, but now we, unlike phi w, which only has significance over the whole of Weyl space, phi p has significance over finite regions of physical observed space, even if it does not have physical significance below the theta scale, which it couldn't do partly because of the smearing and partly because phi w has no such significance. This postulate is a map from Weyl space to space as we experience it that has the right properties. It'll give us, allow us to understand what's going on in a field in a finite region, but not in a region below theta. How does it translate specifically into observed quantities? Well, observed space, well, that's why we appeal to quantum field theory here. Phi p now will appear in the calculations of scattering amplitudes, which are nice spatially located objects. They give us probabilities for finding particles in different directions and are a way often used in sort of quantum gravity and such theories for rendering spatially meaningful the underlying theory. The key point here is, and I'm sorry I've kind of rushed over and still gone over time slightly in this example, there's a key move that's being made here. If one wants to understand where commutative classical spacetime comes, if the underlying theory is a quantum spacetime or something non-spatiotemporal, there's going to have to be some kind of novel interpretive ansatz, according to the one we've just made here, that's going to have to say something about this non-spatial and connect it to the spatial. And we're going to have to take it as identifying what in space corresponds to what in the non-spatial, and thereby explains the appearance of space and the space-time properties that we observe. It's going to have to be novel because the physics that the underlying physics is itself novel. It's going to be an empirical postulate. You may feel it very unmotivated to accept what I've said here, but imagine the case in which the physics that we get out of it turns out to be accurate, then that will provide data support, empirical support for this postulate. And we say one will come to accept such a postulate if it works as part of the theory. But some such postulate is going to be needed. Otherwise, we're just going to be forever in finding it mysterious how the spatial can emerge from the non-spatial. If I had more time, I would talk more about other examples about how that might go and how surprising postulates become to be accepted. But that, I was expecting it to say thank you there. That is the end of the presentation. Thank you for your patience.
Thank you very much, Nick, for this great talk. I will move to panelist, your collaborator. All right.
Yeah.
And the second one being... So let me remind you, if you have a question, please go to the bottom of your screen and click on the Q&A button and write your name in the text box, and I will promote you to the panelist status, and then you can ask your question directly to the speaker. John, as soon as you join us, you'll be the first one. John, the floor is yours.
Oh, there we go. I'm live.
You are, John.
Great. Nick, thanks very much. That was fascinating and beautifully clear as ever. So here's the question. I'm wondering through all of this if there's any empirical access to this theory. Now, at first, you think, no, that can't possibly be the case because the sort of effects we're looking at are happening on a Planck scale or something like that. But then I was thinking, but maybe not. What if we think about non-renormalizable quantum fields, right? If they have a cutoff length, right, a physical cutoff length, that might be manifested physically in something to do with the theory. So anyway, that was just a thought. But the big question is there any way to empirically check this stuff?
So yeah, I mean, hopefully. So one quick note, that CDP paper with the smearing that we referred to actually is that's not directly answering the question, actually is about the renormalizability of this theory. And, of course, one of the reasons people think about this scale is to see if that automatically makes the theory renormalizable. And then there's sort of subtlety to it that I think the smearing is a sort of move they move in to actually make the theory renormalizable. I think, but yes, definitely. So to answer the general question about whether this is sort of empirically observable, yeah, that is the idea that it should be. So there's certainly work to try to sort of see what difference this might make to, say, cosmological applications as well. I mean, which is how a lot of quantum gravity sort of experimental work goes. But actually beyond that, it actually turns out that because there's an invariant area, and so there's a violation of relativity. So, this kind of only works as long as we're not moving, I guess, too fast to the scale at which, to the scale, whatever, at which that's the right area, which is reasonable. But it actually turns out that those relativistic violations really blow up to much lower energy scales than one would expect. So to the point where people have done sort of simple calculations to see that they're already what we already have measured about the validity of relativity already puts bounds on what theta could possibly be in these cases. So yeah. Fedele is here as a panelist. He is the physicist, so he can talk a little bit more if he wants about, other kinds of experimental work. But if you're satisfied, that's also good.
We have time, so please feel free to follow up, Fedele. And
if you are calling me to. Yes, there are people that are thinking about the phenomenology of these kind of things. I think that probably the important thing to say is that the one described by Nick Stolk, or the one described also in the physics papers, is not really what we think would be the quantization of space-time. It's not really the real quantum space-time. There's issues about symmetries. Nick was mentioning something, length or something with change with velocity. So this is really the simplest model, and it's a model that we know well because it's very similar to quantum mechanics. So I can go and look at what I've been teaching for 20 years in quantum mechanics and just translate all this calculation. My undergraduate thesis, the student Lorenzo Leone was really doing quantum mechanics. There are, however, some more refined kinds of non-commutativity where theta is not a constant, it's something more complicated. And there is some work, and I'm involved also in it, in which we try, the important bit is to try to find some phenomenon which amplifies the effect. Typically something which is coming from far away, so distances may amplify the effect. And there is some work. I am always surprised when I talk with the philosophy of science and philosophy of physics, how competent you are about physics. I would like to talk about temperate operationalism in this way. You said something which was very important for us, which is, can this be a model to have a renormalizable theory? Unfortunately not. This kind of model doesn't work. There was the ultraviolet divergences become less violent, so there was some hope for that. But then it was discovered that we were trading ultraviolet with infrared divergences. So it was a good idea. Well, we had it, but still, I say that some different, we are talking about quantum gravity, really. This is what we want to do. And we don't have it, of course. Otherwise, whoever had it would be very famous. But the quantization of gravity should probably also solve some issues about renormalizability. And but that this simple model doesn't work, although it says something in this direction. So this is my physicist contribution to the discussion. Thank you.
Maybe I just add. Tushar will, I think, in his talk, will fill in some more realistic physics, of which this is in some ways a toy model.
All right, wonderful. Thank you very much, Chris. Floor is yours.
Yes. Hi. Can you hear me?
Yeah. Hi, Chris.
Yes. Hi. Sorry, I can't get the video on here. I've got some special circumstances. Anyways, thank you very much for the talk. I enjoyed it. I learned a lot. And I was pleasantly surprised to see, you know, in my own research on Hamilton, as you know, he wrote a book called Lectures on Quaternions. And in that mathematical treatise, he develops a non-commutative algebra. And so it's sort of really interesting to see it at work here in the context of thinking about how to rescue space-time from a kind of underlying space-time without points. But so I had a couple questions. First, a question about motivation. Why is it that we're interested in rescuing classical spacetime or spacetime manifold endowed with points via a kind of underlying fuzzy or quantum spacetime without points? Is there some kind of argument from ontological economy, or was there something metaphysically dubious about spacetime points or a classical understanding of the manifold? Or is the suspicion that our best theories of quantum gravity are or will be ones which treat spacetime as a derivative type of entity and looks down upon spacetime points? So what's the underlying motivation? That's my first question.
I mean, it's all got to be empirical ultimately, right? I mean, this is sort of hypothesized on, if this is the theory that actually gets the experiments right, then what do we say? I think that's really the kind of ultimate motivation here. I mean, there are reasons for thinking that this is, you know, the kind of thing that will actually be the upshot of, you know, research into quantum gravity. You know, theories of quantum, you find this kind of non-commutative structure in theories of quantum gravity, in string theory and loop quantum gravity in certain contexts. So there's that sort of pointing towards this being being a relevant kind of framework. There's also the rather sort of famous arguments that, you know, that try to think about what happens if you if you just take ordinary quantum mechanics and classical general relativity and you try to localize a particle. You know, just maybe think about a microscope where you're trying to find out the position of a particle. As you want to localize it to a smaller and smaller region, you have to use a shorter and shorter wavelength photons to see where you're looking. And at a certain point, there's going to be enough energy just to produce a black hole. So there's sort of these intuitive arguments also that you're going to expect some sort of fundamental shortest scale. And that's what's, you know, and then you find these things also in, as I say, in theory, in string theory, loop quantum gravity. And so this is a way of kind of just sort of implementing that by hand, but you might expect such a structure to sort of show up in quantum gravity. You've kind of given me the chance in a way to kind of explain some of the physical motivations for studying this. So thanks. But ultimately, it's experiment. Would be.
I believe Tushar had a quick follow-up. Let me notice that it's already 1:20 and we have 10 minutes and 3 people in the queue. So Tushar, be quick.
Okay, I'll be extremely quick. To just say, I'm going to talk about this at my talk if anyone's interested in coming in a couple of days. But just to add to what Nick said about motivations, there's a very nice description in a popular paper by Alan Kahn, where he gives an analogy that I hadn't thought of, where he said, take the sort of unificationist motivation of something like Kaluza-Klein, where Kaluza-Klein says you can unify electromagnetism and gravity into sort of the same object if you change the geometry, if you go into a higher dimensional geometry. and you can incorporate all of the relevant symmetries into the appropriate diffeomorphism group for that geometry, for that 5-dimensional geometry.
Yeah.
And then the question is, well, can you do the same thing for the standard model? And well, because the standard model has non-abelian symmetry groups, churning that handle leads you in the direction of non-commutative, this kind of non-commutative geometry.
Yeah,
so that's another motivation there.
Yeah, good. I was going to ask about this, whether I thought that there was some work on how the internal structure of Kaluza-Klein theory could be captured via non-commutative geometries, and the notion of a point kind of disappears in that context. Yeah. Okay, interesting. Thank you.
Right, thank you, Chris. Marianne, the floor is yours.
Hi, thanks so much for the talk. This was really fun. I want to ask a quick question about the emergence of spacetime you're talking about at the end, because I think that's really interesting. And maybe it was just kind of quick and I missed some of this, but I wonder if you'd say a little bit more about what the criteria for success are, in your view, for explaining the emergence of spacetime. In particular, it seemed, I'm a little bit worried that the non-commutative geometry stuff is kind of hid behind the postulates you were talking about, and you mentioned there being sort of alternative postulates. And so how are we going to be able to get are you able in the experimental test to get at really the non-commutative fun stuff behind the postulates, or are we just testing the postulates?
Thank you. Yeah, I'm just going to preface my comment before just by noting I did post the link to the slides if anyone's interested in the chat, if you missed that. Yeah, no, thanks. And I really appreciate this question as well for a little more time to talk about that last slide, because you're right, I did end up rushing more than I kind of wanted to there. So the way I would think about it is that it's really a sort of whole package. So one would have the non-commutative geometry in the background, and say that there's one a theory one has in mind, and then different postulates about how that might connect to commutative geometry and sort of classical, how one would recover the space-time theories that we have now from that. And so one could, if one knew the non-commutative geometry, then consider different postulates and sort of test, that comes with a particular claim about how to map, how to make the map, how to produce the fields. And, different maps would have produce different fields, presumably with different empirical outcomes. Of course, that would be if you already knew what the non-commutative geometry was. So I assume the problem that you're saying is, this is going to be a kind of, I think there is going to be a package there, and maybe there are issues sort of under determination that tweaks in the, I don't know anything kind of concrete, but sure, it's another postulate. So the bigger the package of postulates, the more opportunity there is for sort of under determination. Yeah. Is that the kind of direction you were? Yeah, I don't think it's going to be just testing the postulate. It's going to also be, sensitive to the underlying physics as well.
Great, thanks.
Thanks, Marianne. Mike, go for it.
Hi, Nick and Tushar. I have a bunch of scattered questions, but I'll restrict to one question, or maybe it's a set of questions. But so I really appreciate the distinction or the comment about how this is somehow a global physics, but really what we want in some sense is a localizable way of talking about things to map onto the project of physics as we've historically conceived of it and so on. And I'm wondering whether you've thought about the story that you were giving on the last slide in a slightly richer context, where in addition to wanting to get points, we also want to get restriction to maybe, so sometimes we want to get a restriction to a localizable region in space. Sometimes we want to get a restriction to a lower dimensional hypersurface. We want sort of a topological physics of surfaces in the laboratory. And so this is also a kind of spatialization of physics, but it isn't recovering points, it's recovering some sort of dimensional features or topological features of space. And I'm wondering, this model that you've presented is simple enough to get traction on, but I'm concerned that it might be so simple as to throw away the richer parts of space that we do want in a local physics. Does that make sense? This was harder to articulate than I originally.
Can you give me a sort of more concrete example? I think I understand, but a more concrete example of when we might want that?
I have in mind maybe certain models that we have experimental traction on in something like condensed matter physics, where everything that's going on, or at the level of description we care about for the experimental system, everything that's going on can be understood in virtue of there being this material system that is fully adequately described as a two-dimensional surface. In in three-dimensional space or in four-dimensional space-time, there is this surface that persists, and so it's localized, but it's not localized to regions, to regions that are centered on points so much as it's localized to hypersurfaces.
Right. So Fedele may have some more precise things to say, but I think maybe I can at least sort of clarify a few things. So I was so in the physics we're talking about here, it is just space, so rather than space time, but you're still talking about sort of restrictions to surfaces in space. I also want to be kind of clear on the last slide. Although that CDP map, smearing, gives you field values at points, I want to kind of emphasize again that we're not really recovering points again. I mean, we're going to end up with a field that makes it sort of look like we can recover points, but there really isn't any sort of physics there. So, it's about recovering finite area, finite regions, finite areas, because if we're talking in two dimensions, finite volumes if we're, talking in 3 dimensions. And then for the surfaces, so I don't know anything about what. So you'd have to be sort of thinking about a 3-dimensional commutative geometry and its sort of restriction to or higher dimension and restricted to a 2-dimensional. Sort of the thing is, it is the analogy with quantum mechanics sort of works. So, if you try to, it would be kind of like trying to cram something, localize even to crush out 1 dimension would be to try to localize something, as it were, into a sort of point from respect, a point. But that leads to sort of expansion in the other direction. So you can't sort of localize things. So you'd have the same sort of thing happening here if you tried to localize sort of you're going to get sort of things blowing up in other directions. So if I could, Fedele, do come in, but I just want to sort of say, so I think to get the kind of thing that you want, Mike, you would first go, I just finished, you would first take it to the classical case, and then you can kind of localize, but I assume, whatever you're doing there, that's a good question about exactly how it's sort of representing the 3-dimensional physics, how one would sort of try to understand it. Fedele, you want to have if you understand?
Quickly, for the example Mike was asking, a 1-dimensional solid state, 2-dimensional, something which reduces to 2-dimensional, still has the width of an atom, because they are atoms, it's a 1-dimensional layers of atoms, and this is very big. So we are talking of localizations which go well beyond the localization of atoms. because an atom compared with Planck length is much more. So from this point of view, there isn't, it's not a counterexample. So it's two-dimensional because everything goes on only with X and the X and Y component. But there is a Z component, which is the size of these atoms that they move around. So
okay, so the broader, the conceptual overview is you get back more robust classical notions of spatial geometry before having to answer questions about in virtue of what we can idealize these particular physical systems.
The limit of h bar going to zero. No? The limits are not very simple, but we have a way of seeing classical mechanics from quantum mechanics. But there is a good example, which is loop quantum gravity, which is some sort of complicated non-commutative geometry. But loop quantum gravity has the problem that it has is that it's difficult to see the quantum space, classical space-time emerge from their theory. So loop quantum gravity is an example of a non-commutative geometry. In fact, we do very often joint meetings, and I did dabble a little bit in loop quantum gravity, but there the problem is the opposite. So you don't know where is space. At some level, we know that I am here in Naples and moving around. So I'm classical. It serves us well. And so I have to find some limit, the classical one. Okay, time is really running.
We are actually reaching the end of our meeting, but we'll give Ed a minute since he nicely joined us. Ed, good to see you again. And you have a minute for a question. And Nick,
I'll do it real quick. Great talk, Nick. I really loved it. I loved the conference over the last month. My question is about, as you would imagine, substantivalism, the kind of issue you brought up at the end. I'm not quite sure if I understand the mathematics right, but do you need the continuous manifold to set up the functions that would lead to your non-commutative geometry on there? Because this is the argument I was thinking. I figured that John actually would answer this question, that I could see a manifold substantivalist saying, well, you need the continuous manifold to set this up. And then you try to kick the ladder out under you and say that in the epistemic case, it's unphysical. And I could see them arguing, this would kind of be like maybe Smolin's argument that this whole approach is like continuous topologically dependent. And so therefore it's not truly relationist, right? It's still substantival in some way, but maybe I'm totally wrong on that.
No, very nice, Ed. And it is very nice that you could come to see you here. I'm sorry we didn't get to sort of overlap our time together.
We're kind of catching on to it right now.
But yeah, well, first and then second, I guess I'll invite you, if you want to be a substantivalist, invite you to be a sort of algebraic substantivalist instead of a manifold substantivalist. Just two things because we're quick. I mean, I do want to sort of propose that you just think that you really can think of the ontology as sort of abstract compared from a spatial point of view, that it would just be this non-spatial structure, and the space-time is representational. And I think that kind of that does make sense. But one concession, but I don't think it's kind of helpful for pushing the metaphysical point is, I've still got to tell you what the algebra is. And the natural way to do that is in terms of actually giving it in the Weyl representation, because now I actually have a framework where I can kind of tell you what the algebra looks like and what the manifold is. I can kind of encode all the algebra. The algebra I gave you is sort of misleading, is in a simple example, because it's finite, and I can just basically give you the table for what what that function does. If it's an uncountable algebra or something, I have to have some way of telling you what it is. And in that case, moving to the Weyl representation, I need to do that to tell you what the structure is. But I don't think that carries sort of ontological weight to get to sort of substantivalism.
Yeah. No, it seems like it's a kind of a question begging to say, even if you need the structure, to say that it retains the normal ontological importance we would give to it. So that makes sense. But I'll have to read your paper and see how you guys discuss it,
All right, great. I think we will leave it at that for today. Thank you very much, Nick, for this great talk, and thanks to Fedele and Tushar for joining us for the Q&A, and as well as everyone who joined us for the discussion. Thanks, Ed, also for joining us today.
Great seeing you.
Thanks again, and we hope to see many of you on Friday for the next lunchtime talk in the philosophy of linguistics. Bye, guys. Have a good end of the day.